So yeah, so I did a presentation last time, and yeah, so I finished telling you that I will try to implement our own version of a turbulence model for RANS turbulence model. So what I have planned today is I will.
Hello,
Hello.
hello, can you hear me?
Yeah, I can hear you.
So can you this hide this thing that stop sharing is written at the bottom?
Ah, right. Okay, sorry.
Yeah,
Yeah.
you can.
Okay. So thankfully, I can hear Pratyush's voice, so I am able to connect on my audio. Anyway, yeah. So I wanted to talk about how to make our own turbulence model in OpenFOAM. And as we are using OpenFOAM 6, I'm using OpenFOAM 7, but this implementation is the same for both the versions. So it is actually a bit tricky, and I would like to show you this by showing you the turbulence models folder in foam src, and it will become clear that it's not very straightforward to actually compile a turbulence model, and we have to kind of do it in an indirect manner. So it will become clear when I show you this thing. And primarily what we'll focus on is just how to compile a model. The idea is to also implement our own model, so we should make some changes to a model and then see the effect. But for that, you actually should have a turbulence model in mind to do that. So as I don't have that, I'll try to first get the compilation process done, and then if I have time, because this is going to take a while to explain everything, and if I have time, I have a document that I will refer where a turbulence model has been implemented, where a slight change has been made to some of the terms of it. And that model is a filtered version of k omega. I myself am not familiar with it, so it will be a new challenge for me also. But more importantly, what I have done before is compile a turbulence model of my own, and I know that this can be a big headache too. So let's just try to overcome the first mountain, and let's see if we have time to overcome the second one later. So compiling a turbulence model from scratch is the main idea. Okay, so I'll just connect to my system, and what I will do is I'll first show you um, how a turbulence model gets compiled in OpenFOAM. So this is your main, so this is OpenFOAM 7, 6 is pretty similar. And in SRC, you have turbulence models. Now, compressible, incompressible, and turbulence models, these are the main sort of folders in here. The other are related to if you are running a multi-phase simulation. For us right now, this is not relevant. So uh, the main codes for K omega SST, K epsilon, these are in this folder. So as you can see, within the main turbulence model with capital T, there is a small t turbulence models. And then inside that, there is a folder called RAS. And here you have all these models. Um, is there something? I heard somebody
No, no,
unmute.
no, no, no. You can continue.
Okay. Yeah. So this is where the models are. And what you would expect is, so for example, let's look at k omega. You have a k omega dot c, k omega dot h. Typically, what you would expect is there will be a make folder somewhere here. So there is no make folder here. So let's go one level up. There's a make folder here. Good. So what I'll expect is, okay, in the make folder, there will be a files where I will see a relative name for this location. So this make is in turbulence model. So I would expect a make files will have one entry which says RAS slash k omega dot h. So it will make the k omega dot c file. But if you actually look here throughout this folder, there is no such entry. So I'll even try to find it. So there is no k omega dot c or any such file, right? So that means that there is some other way in which this model has been implemented. And What I'd first like to do is sort of give an explanation for why that is. And for that, we need to understand what turbulence models generally are utilizing. And um, let's see, this is the .c file. Okay, I'll just close everything first and then, yeah. So as I said, this is the main folder which defines the turbulence model classes. So for example, it defines a RAS class, it defines an LES class, laminar class, eddy viscosity, linear viscous stress. These things are all sort of important in terms of figuring out what new T should be that we'll add on new, and even new will come from this laminar. And the main file here is this turbulence model.c and turbulence model.h. So this is the class definition for a turbulence model. And you can see that it inherits from a dictionary. So the reason why it has a dictionary as a parent class is because we want it to be able to take input and output during runtime. But anyway, so you have this as your main model, and the issue is that it's supposed to be able to run with a compressible version, an incompressible version, and with different transport models accordingly, a compressible transport model or an incompressible transport model. So why that complicates matters is because when you are trying to implement a turbulence model, you cannot simply make a k omega. It has to be a k omega with a template. So if you are not familiar with it, I will say that it's something equivalent to when you are going to buy a car. You have to sort of go and ask them that I'm going to buy a car with a specification. So it has to be a car with a manual transmission, or it has to be a car with a automatic transmission. So it's somewhat similar. You can't just make a k omega. You have to explain or also specify which k omega you want to make. So it has to be when k omega is created, it has to be sort of created with a template, meaning it should just say that this is k omega and it runs with any transmission. So as you can see here in the definition for k omega, there is a template defined called basic turbulence model. And then all of k omega's later definitions are based on a template. So a template is kind of exactly what I said before. So you are saying I'm making a k omega, but what I will do is, so whenever you see this bracket, and whatever is inside that is sort of a variable, or it can take variable definitions. So this is the reason why the implementation of these models is not so straightforward. So what has to happen is you have to have a k omega which is implemented with both with every possible transport model, and every possible or even within a transport model there are other options. Like even within incompressible and compressible transport models, there are several different options. So it should be able to compile with all of them. So that is the reason why the overall compilation is indirect. Now what I'll tell you is where exactly does it actually get created. So for that, this is this is my main folder, and this is where the source file for k omega is, for example. Now it actually gets implemented within this folder. This is compressible, and within compressible there is something known as turbulent fluid thermo models. So inside this there is a file called turbulent fluid thermo models.c, and then here is the only place where you will see there is actually a reference to k omega or k omega dot h or anything like that. So this is where all those models are actually. So for example, include k omega dot h, make RAS model. So make RAS model is sort of a set of commands. It is sort of proxy for a set of commands which actually create a class. So this means that if you actually want to implement your own model, you need to kind of have this structure, as in you need to have a turbulence models with a capital T folder, and you have to have a turbulence model. Inside that you have to have a RAS folder, and then instead of k omega you will have a my k omega, and then in the parent, the top directory Turbulence models, you should have a compressible. And then in the compressible, you will have to have this folder, and then you will have to have this file. So this is the whole sort of idea. I'm trying to create only, this structure, but I will not have all of these things. I will only have the things that are relevant to me. So I will start by creating this folder, the main turbulence model folder, and then I will make uh, compressible and turbulence models inside that. So I will do that now. And what I will do is I'll create a new session, and I'll go to the run folder, which is my main folder. And here I will make a directory called src slash turbulence models with a capital T. Okay. So actually, it's much easier if I just show it here.
Then please little bit zoom out your terminal.
My terminal, zoom out. Oh, okay. Is it? I hope this is okay. Anyway, so as I said, within my run folder, I created an src and then turbulence model. This is empty now, but what I want is I want this structure inside here. So I essentially want this and this. Only these two files. So I will just do that now. Is there a doubt? Yeah. I can't hear anything clearly, so I'll just continue. Okay. I just keep hearing as if somebody's trying to say something, but okay. Oh yeah. RAS slash, let's call it, no, let's just make this folder first. So I have this entire structure now, wherein I can put a model. So I can copy paste it from here as well. So let me just do that. And similarly, I will make a compressible slash, let's take a look at where that file was. It was in compressible and it had this long name, turbulent fluid thermo models. Oh, sorry. So this is just the directory, and yeah. So this will also have been created, and I basically need to. I'll just, yeah. This is the file. Okay. Actually, I'll just double check that. Yeah, this is the file where I have the implementation of k-omega.h. So what I'll do is I'll copy this here. I can do this by the terminal also, but I kind of need you to understand what I'm trying to do visually. Okay. So this one on the right, this is the actual OpenFOAM SRC. And this one here is within my user directory. So I have these two files because these are the relevant files for the implementation of k-omega. And I have this. I have a RAS folder. And here I have Okay. Now actually, okay, I can rename this here as well. Let me just call it my k omega. Now, these things you might even be familiar with in terms of terminal. You can just use MV and all these things. But for now, let me just do it like this. Okay. Again, I can, within these files, I have to rename k omega everywhere with my k omega. I can do it with stream editor. So SCD space minus I and then whatever substitution you want to do. That is possible. But what I want to do is actually show you where all this actually has to be changed in the file. So for example, I can do it with find and replace here, but I'll just do it manually. So first you have a sort of, this is called a header guard. And you should ideally have a header guard around everything that you implement on your own in OpenFOAM. So this, if not defined, whatever your sort of proxy name is, then you define. So it's a way to make sure that there are no double definitions. Anyway, so right now I'm literally showing you where all this is. So in first instance is in the header guards where I need to make a change. Then in the name of the class, again here also I think you can change the name. And let's see, in the constructor name, in the type name for sure. Again in the destructor. Okay. Finally here. I mean, this is another sort of a guard where you make sure that if no repository is defined, only then you include this file. Anyway, but as you can see, the typical places you make a changes in the name of the class, and then in the type name, which is generally how it will be identified once you have compiled it, and yeah, in the name of some of the functions. So now I'll do the same thing here. Again, I want to show you this can be done with SCD command much easier, but I'll just do it manually. Here I will at least do a find and replace so that we can find all the instances much faster. There'll be more instances here because in the definition of all the member functions, meaning the functions that the class uses, there you will always have this name. So there will be far more instances of this. Okay. So we'll do find. Okay, this one we definitely need to replace. Yeah, so as I said, there is a correct NUT function. It's there in every turbulence model, but here obviously it says k omega, but it's now supposed to be my k omega. So we'll replace this for all the functions. This also needs replacing. Template class. Okay, this is all fine. Again, this needs replacing. Yeah, that's it. So about 7 or 8 replacements we made. Right. Okay. So now we have this part sort of sorted. Except this part is not. So what we'll do is we'll change this name also. And we'll just put a my here as well. Because this sort of, even though this is a different directory location, I don't want this name to clash. So I'm just changing this to my turbulent fluid thermo models. Okay. And what I will do here is I'll remove all of these. I don't need any of these to be recompiled, even though it won't necessarily do that. All of these have header guards around them. I will add the name of my k omega here. So here this is the name it will be identified by. So make RAS model will actually just run. I mean, it will add it to the sort of runtime directory, and mainly it will make it accessible to our main solver, and include my omega .h will actually create. I mean, it will actually compile the class. So this is the only place for other models as well, like in this indirect way through this file turbulent fluid thermo models.c, that it has been compiled. So we've got this structure down. Now the issue is, as you can see, we have to call, for example, this header file. Now that means obviously we will need a make directory with options. So we'll again look at how this is structured here. So you can see that uh, this folder doesn't have any make directory, and it is here. So what we'll do is we will also do the same thing. Within compressible, we'll copy this folder. And we leave the options as it is, because we know already that to compile all these things, we do need these dependencies. We need these include, and we need these libraries. So we will not touch options, but in files, obviously this files is for this particular folder for compressible. So it's going to try to compile all of these things. We don't need to compile any of these. We only need to compile the file which is inside here. So what we will do is we will yeah, we'll remove this, and we'll remove all of this. None of this is relevant to us. This file is what we are going to compile. We have changed this name, and we'll add it to user lectin. And again, the library that it will create shouldn't be compressible turbulence models. I don't want it there. I want to make sure it's something different from the main source code. So I'll add a different name here. Okay. So, okay, where are we now? Let's see. We'll just once more recap the structure. We have turbulence models here as well. We have RAS, and here I have my k omega, where there was k omega, and it will be compiled by this file. So this is the original implementation in which it was compiled here, while here I'm going to compile it. So I mean, I can just delete all this, but anyway, this is also fine. This is where I'm mentioning that I want this bit. Okay. And the other change that I made was I copied the make directory from here, brought it here. Options I retained as the original file, and the only change I made was in this. I changed the name even in the folder, and then I changed the location where it will be created, and I also changed this name of the library that will be created. So I hope these changes are clear. Okay. Now we can think about compiling this. Okay, but before that, what we need is we need also an ln include like is present in this folder, so that all the necessary files that will be needed during compilation and linking will be available in the ln include. So what we'll do is we'll obviously have to set the environment, and so we are currently in compressible here, and what we are doing is we are creating the include folder one level above compressible in turbulence models. So linking include files. So now we have this. So we have the whole setup. Let me see what happens. Okay, so it's unable to find something. Turbulent fluid thermo model.h. Let's see why that happened. So this file that it's complaining about, turbulent fluid thermo models.h. Let's see where that file should be. So as I already mentioned, this should simply be here. Turbulent fluid thermo models.h. So I would expect it to be in the ln include of this folder. Yeah, so it's here. So if we have this in our ln include and in the library that was created in the libs, then we shouldn't have this problem. So we'll just check in the options if we have that. Yeah, we don't seem to have that, right? Okay. What we will do is we will add it here. libsrc / turbulence models / compressible / ln include. So what I've done here is I simply gave it the folder where it should be looking for header files, and which is this folder. So within src turbulence models compressible ln include, this has this file. So now it should not complain about this file, but I also need to include the corresponding library that will be created. So I'll just check the library that will be made. So it's called compressible turbulence model. So I'll just check if I have that here. Oh, I actually didn't even save this. Okay. Yeah, so I don't have that either here. I have a compressible transport models, but as you can see, I don't have this compressible turbulence models. So you have to add L to indicate it's a library. And let's see, I hope that we move past this error now. Yeah, we moved past that error, but we got a different error. And this error says we don't have this file. Now, where is this file? So this file is actually here, right? So this is turbulence model H, and this is what it's looking for and can't find. So we'll see where this has been included. So it should be, so there is a make here. There should be an ln include here. And we expect this to have the turbulence model.h. Here it is. Okay, so then now I need to include this as well. So let's do that. Oops. Again. And just to make sure, within turbulence models, you have turbulence models and then ln included. And I also need to include the corresponding library, which I think is here, but I'll still just check it in the main file. So for that, what you do is you go to the directory where it was made, you go to the make, and then you see in the files, there should be a mention somewhere of what library has been created. So lib turbulence models, when you actually are linking it, you don't use the entire lib, you just use L turbulence models. So I believe this was here. Oh, sorry, options. L turbulence model. So this is there. Again, after including that, I hope we move past this error now. And let's see. So you can see it's taking quite a while to compile. Okay, it has compiled, but again, now this is interesting. Typically, what you will expect is if I have made a turbulence model and it's called myk omega, what I'll expect is I will have a .so file named lib myk omega. But actually, that's not what happened here. We didn't compile myk omega directly. What we did compile was this thing. Oh, we compiled this thing. Hence, this is what we actually made. So we will get a my compressible turbulence models .so as the final sort of binary that we'll have ready. So lib my compressible turbulence model .so. So I bring this up because, okay, I'll also show you where this gets actually created. So generally where it gets created is you have this user directory, there will be a platforms folder. This will specify what operating system and what bit size you are using. Within this, there will be a lib folder, lib my compressible turbulence models.so. So this is what, okay, I shouldn't have tried that. Okay, there will be a complaint now. Okay, this is essentially a binary file. I don't know why I double clicked on that. Okay, I should immediately cancel. Okay, sorry about that. Yeah. So this has been created. Um, the reason why I bring this up is now let's say there is a change you want to make, which is what we'll do later. So when we want to make a change to our main turbulence model, we should keep in mind that we are not actually going to make changes to that, or rather we are not going to compile the model directly. We are going to compile this file. Essentially, we are going to compile this file, right? So when you make changes to your turbulence model, which we'll do, but just keep in mind that what you'll have to do is you will have to regenerate first of all your include files inside this. This has to be re-included. So this command will have to be rerun if you make a change. And secondly, the actual file that has to be compiled has not changed. There is no change that has been made to this file. So by default, the compiler will not compile it. So what you will have to do in that case is you will have to do this command touch and that file. So when you do this, it changes the sort of current or the date attached to the last modification for this file. And then the compiler knows that some change has been made to this file, and then it will recompile. So just a small thing to be kept in mind regarding that. Anyway, so what we'll do now is we'll try to run this case or run this turbulence model. So for that, I can open. Why are there so many terminals open? Okay. Okay. So oh, I can't. Okay. I'll just open another terminal and increase its size, and again set my environment, go to run. So I had, okay, in turbulence models I had done a lot of tests, so I'll go there and okay, I will make a new folder. I remove all this time folders. Oh, so the time folders are gone. Oh, there was something, I'm not sure if. Okay, start from start time. I generally, I mean, in all tutorials they have this, but I prefer it to be latest time. It's not relevant. But more importantly, we have made a new binary, and by default, um, the case folder will not know about it. So what we will have to do is we will have to indicate that here. And this will be the name of that. Okay, this as in this name. Oh, sorry. I hope the name is correct. Anyway, we'll find out. And hopefully now this will run. I'm not completely sure myself, but let's see. And okay, so this thing has not been recognized. My k omega is not recognized. Okay, let's see. So there is a trick. I was not sure if I'm also not completely aware myself if this will work. Um, so there is a reason why this happens, but it's too complicated to get into, and it happens with my only k omega models. So the way to get around it is to actually compile a k epsilon version also. Um, although um, you know what, I did this compilation just before. Let me just check. I'm missing something else here. Mm, yeah. So, oh, did I miss a level? Okay. Turbulent transport models. That doesn't look right. Anyway, let me just take a look at my structure here. We have a compressor, we have a turbulent fluid thermo models, and in this we have our k omega. So as you can see, I'm just trying to mimic this here. Um, I'm just making sure there's not something else I have commented out. Nothing else. Okay. And now obviously I don't have a my k epsilon, so I'll have to do that whole process for k epsilon as well, which is essentially I go into SRC, I go into turbulence models. Where is k epsilon? This is k epsilon. So I will, if this works, then I will try to explain why it works. If it doesn't work, then we still have a challenge on our hands. Um, right, and I'm supposed to copy it in this same structure. And I will rename this to my k epsilon. Okay. Okay. Again, now I'll just do a find and replace. Oh, did I make a mistake? I think so. Yeah. Okay, okay. So I have already added additional names where I shouldn't have. I believe all of them are done. Right. All the instances are replaced. And I have to do something similar here. I don't want to change that or that. This is okay. I'll leave that as well. Okay. So I have this ready, but I don't have it here, right? So what I'll have to do is this, which was our main compilation. This one, I believe. No, this one. Okay. So okay. So now we should have these additional files here. Yeah, we do. And let's just minimize this. Now, as I said, we have changed something in the files that we want to compile, but in the actual file that we will be compiling through make/files, there is no change. So we will have to do this touch. And now let's see. What does this say? Constructor, destructor. Okay, did I make an error somewhere here? Oh, I did it. The name was supposed to have a capital E and a small k. Okay. Hmm, what is the error saying? Um, so it says expected constructor, destructor, or type
Check
convert.
my kepsilon.c file.
The my k epsilon.c file. Ah, okay. You mean I have made a naming error somewhere here? Um, I don't think so. No. In any case, it's not complaining about that. It's complaining about an error here. It says it's expecting something else before make RAS model in here. Myk epsilon dot h. Did I get this name right? Myk epsilon dot h. This seems okay. Myk epsilon is the name I want. Oh, right. So that's the mistake. Sorry. That's the. Yeah. So just the case of RAS was incorrect. It should all be caps. Leave my compressible turbulence models dot so. Okay, I don't know if this will work, but I think it's like a hack that works sometimes. Oh, sorry. Where is the file on which we are running our case? Well, okay. So what I will do is I will try to follow the structure which worked for me. I know this is not ideal, but compiling a turbulence model is a nightmare. So what I will do is I will just try to see if this compiles. So as I said, I was doing this exercise before, and I had this roughly exactly the same set of files. Yeah, I think this is exactly the same. My compressible turbulence models, everything is same. However, there is a slight difference in that there is this layer, which is actually in the incompressible folder. But anyway, I will see if this hack works, and then we'll see if I can figure out why it works. Okay, first of all, in this I don't want it. Where is the compilation folder? Right. Do I have the same set of? Yeah. Okay. Okay, so this has compiled similar to what we had before. Just want to make sure I'm not making an error with the include name in the. So this is the library which has been created. Oh, am I making a mistake in this? Okay. Actually, there might be a very silly mistake I'm making. Okay, let me just open another one. Yeah. I was running this. This seems about right. Okay. This is not the issue, seemingly. Hope I didn't make any mistakes in this name. Turbulence models.so. No, I don't think so. Okay, so this runs. So that is kind of interesting that now this is running with our turbulence model Mike omega. Actually, I mean, I can probably even show you in this. Yeah, I mean, you get this double definition complaints when you compile your turbulence model. But yeah, I mean, it is selecting the RAS model that we just created, and it is running that. So the interesting part is now I'll try to figure out why exactly this compilation worked and the other didn't work. Might be that I have slightly different set of uh, files and options. So I'll do that. I'll try to get it to compile with this folder rather than this folder. But for that, um, let's just close everything for now. For that, I'll have to understand what is the difference. So one difference is the name of this. I don't think this matters so much. I think it's probably got to do with something that has been included. Actually, I don't like this view. On this new window. And this here. I don't believe the name of these folders has anything to do with it. Yeah, these names are exactly the same. I believe the contents of it are also the same. Okay, I didn't even have to try the k epsilon hack here. So then the reason has to be this file. Let's take a look. I don't think, again, then this name is different because of a difference here. And this name is fine. So even this files is not the problem. I suspect there is something different in options. Okay, there are a bunch of more. So all right. Oh, okay. I think so. I think I understand what the issue is. Right. So I should have included the incompressible turbulence models as well, because the case that I'm running is actually based on the incompressible. Simple form is an incompressible solver. So if that is truly the reason, maybe this should work then. I will just include whatever is missing from here. So I think this is not there. And let's see what else is missing. Finite volume, compressible, and everything else seems fine. Okay, again, here the library for the incompressible models is there. We don't have it here. So let's try to include this. Okay. So Now, if that is the reason, we should be able to compile again with this one. So I will rename this to works. Let's say works, and I will rename this back to. Oops. Okay. Now we can do the compilation again. Okay, so that clears out the compilation that was done before. I actually don't want the compilation of k epsilon. Let's see. Yeah. Okay. Right. Okay, so the reason why this takes a long time to compile, even though it's just one file, right? It's just k omega dot h and k omega dot c, is because it has, because of those template things, the fact that it's going to compile one version with a compressible model, one another version with an incompressible model, and there are also within those there are some options, like if you have seen the constant slash transport folder, there can be different sort of transport models also. So essentially, when you have something like this, if you are familiar with what templates are, um, when it actually comes to the compilation stage, the compiler compiles every single version that may be used. So that is why the compilation takes a long time, because at the back end it is making a k omega my k omega version with a compressible model, with an incompressible model, and within compressible models different transport models, and within incompressible the different transport models. So that is why it takes long. Now let's see if this continues to work. Okay, so that wasn't the problem. So what was the problem? Okay, so I did compile a different version as you just saw, and it still doesn't work with this. So that's interesting to me. Don't worry, I'll share all of these directory structures with you, both the ones that work and the ones that don't work. But nonetheless, this is something we should be able to figure out. Don't think there is any difference in this. I want to check if I've missed something else here. Okay, actually now we are sort of, because of the naming problem, I mean renaming, there is a problem here. I mean, it may not be very interesting, but if you have actually tried to compile anything, you will realize that this is most of the time that it takes. Like, you have an idea what you're supposed to do, but you face all these errors. So it's been a long time since I compiled any turbulence model. So that is also why I am also back in sort of square one position here. Anyway, I just give it one try, and if not, I will just move on to trying to make changes to the my k omega and recompile it. So this was exactly same. So this is the works folder, and this is the compressible folder. Okay. I mean, I have half a mind to just copy that here, but then I will not be able to figure out what caused this. So that is why I am not doing that. Turbulence models in compressible include, and I have that here as well. Turbulence models, compressible turbulence models. That I have here. One, two, three, 4, 5, 6. And what do we have here? Well, looks the same to me, unless I've missed something. Fluid thermophysical prop models. Incompressible transport models. Do I have this? Oh, I don't have incompressible transport models. Let's see. And so there we have a compressible version of transport model and turbulence model, incompressible version of uh, turbulence model and transport model. So I believe that we have here as well a transport model, and two turbulence model versions. You will always have finite volume and mesh tools. So you have those two here. You have the library for turbulence models, which you also have here. And then these are related to, again, the compressible transport. These three. Okay, species also there. I don't know if, yeah, I have it here as well. So if I was correct, then that should solve it. I was missing the incompressible transport versions of this. And again, now the thing is this, I'm not sure if this will recompile on its own here. Oh, it is recompiling. Oh yeah, that's because I made a change to the file slash options. Okay. Well, now I'm really confused why this is happening. As a last hack, should really just copy paste this and see if this works. No, I shouldn't do that. Actually, I'm not sure if this works here like this. We will see. I'm not sure if this works, but, or you know what? We will do one thing. We just rename this file in the other folder. Oops. Oh, I'm in the wrong folder. just copy paste this here and see if this makes a change. Yeah, just to be clear, this file is exactly the same. And as this file. Yeah, I don't see a difference. Anyway. So, so I'm just recompiling it, but I mean, if options is the problem, file/options, this shouldn't work. Yeah, so then the problem lies somewhere else in the two implementations. Okay. You know what? I'll just share the working version for both with you. But before that, we have to sort of compile it the way that it's working. It's a bit hacky, but yeah. Not this. Oh, what happened? Did I break everything? Oh, it's not. It hadn't finished compiling. Yeah. Okay, I'll do one thing. This clearly works and the other one clearly doesn't work. I will try to figure out why that happened. But essentially, you are able to compile a turbulence model. And now what we'll do is we'll try to make changes to this this set of files, these two files. And for that, I will refer to okay, I will refer to this document. I'll also share where I got this document. This is from Professor Hakan Nielsen at Chalmers. He's well known in the OpenFOAM circles. So he has shown some changes that we can make to a k omega model. He's done it to k omega SST. I don't think that will make a big difference, because we are just trying to make changes, compile, and see if the thing works fine. So what we will do is, yeah, so yeah, as I can see, this is where he talks about modifications to the new model. So here he says the first thing you should change is the correct function, correct the turbulent viscosity. Okay, so he says at the end of the class declaration, you can. Oh yeah, by the way, so the reason why I have to pick somewhere is because if you want to implement a new turbulence model, you should have something in mind to change on the standard models. So I don't really have anything right now that I'm working on with regards to turbulence models. And so I'm just kind of showing you what all you have to do to compile one, and then changes you can always make based on whatever physics you are trying to capture. So let's see. He says you add this in the .h file. So we'll do the same thing. Okay. Well, this is already there. And this is not a problem then. So this is the change in the definition of the correct. Okay. Let's see. So what he's saying is, you have this my k omega, and it has a function called correct. Oh, actually, why should I not? Okay, yeah. Let's do this as well. Before we do this, let's just talk about where the simple form is going to be using the turbulence model. Let's do that. Where is the main OpenFOAM directory structure? This one. Okay. So you have applications, you have solvers. I mean, you can do these things even in a terminal, but sometimes it's easy. It's better to just show the directory structure from sort of a top level view. And so we are using simple form, which is an incompressible solver with turbulence, right? So what we will see is this is one of the places where it uses. So div def ref. So this is the momentum source term that is added. This actually comes from this. I should show you. Yeah. Dev row ref, div def row ref. What is it that we have here? Div def ref. Okay, I think I've gone to the wrong version. Yeah. So in an incompressible turbulence model, you have div def ref. So it's defined here. So this is your main turbulence model folder. Within incompressible, you have the definition here. So this is the declaration of that. And this is the actual definition of that. Where is div def? Oh, right. This is a virtual function. So then based on whatever model you are using, you can have different implementations of this. So essentially it gives the divergence of the deviatoric strain multiplied by the effective viscosity. So that is why it has this name. In this, you can roughly, I'm not sure if this will have the sort of implementation of this, but let's see. So that you get an idea of what exactly it's trying to do. Oops. Right. I think this will have the implementation. Okay, so it has it for the compressible version, but essentially you can see that it's trying to multiply the new effective by some terms here. This term is grad u transpose into dev 2. Now I can go into where where you'll find the definition of all this. This is actually in primitives, so it will go very high up in the chain of OpenFOAM. But essentially, this explains the momentum source term that you will have in the U equation. And what it does is it's essentially grad U plus grad U transpose for incompressible version. It's grad U plus grad U transpose multiplied by new effective, so new plus new t. And in the compressible case, you also have another term here, so it will be new effective into grad u plus grad u transpose minus 2 by 3 the divergence of velocity. So actually you can split those two terms and then you get a Laplacian term and you get this divergence of deviatoric stress basically. So the minus 2 by 3 term goes into the Laplacian and this gets, so I'm just trying to show you that all the answers regarding whatever is defined even in simple form regarding a turbulence and this, so essentially this is pointing the fact that turbulence is a pointer and it points to some function. So you have this arrow and then the object of turbulence, which is the turbulence model, will be able to return this value. So this is the momentum source term. I think besides this, you will also have a couple of other places. Let's see. I believe there is a turbulence here as well. Yeah, so okay, so here it creates the turbulence model. Again, turbulence is created as a pointer. So you can see it when you initialize turbulence, it initializes as a pointer to an object. So this is related to memory management within OpenFOAM. Does it have, so this is in the, yeah, in the main simple form also, I think there will be some instances of it. Yeah, so you can see turbulence dot correct, right? So when you run your solver, you will have a laminar transport correction, which will essentially add the viscous source term with nu, and then you will have to add one with nu t as well. So that is what this correct does. It updates the nu t value, and this is exactly what. So there is also a validate function where it just like at the end of the previous iteration, it needs to update it before doing the next iteration. So that happens here. And then this is the last place where simple form uses turbulence. So here it corrects, which is essentially solving nu t based on the updated velocity values. So this is what the change that Dr. Nielsen wants us to make. So he's asking us to change this correct function, which is basically going to change how this step is being affected in simple form. So you essentially solve U equation, you solve P equation, and then you solve the turbulence equations. Let's see if it's visible here. Yeah, so you solve for ux, uy, you solve for P, and then you solve for omega and K, right? So that is essentially after you solve ux, uy, then you solve for nu t, and then you solve the K omega equations, and or sorry, you solve for ux, uy, and then you solve for K omega, and then from K and omega, you will get a value of nu t. So that is what correct will do. And I believe he's just asked us to completely copy the correct function. So he says, right, Okay. Oh, even says compile and be prepared that you will get lots of error messages. Omega was not declared in this scope. I actually am looking at this for the first time myself, because it's difficult to find a turbulence model to implement. Anyway, let's just try this. Oh, I am using k omega, my k omega here instead of k omega SSTF. Yeah, let's just close simple form. Let's close where we saw the definition of digraph and all those things. Where is our case? Okay. It is here. Oh, what am I doing? Just lost my way. Sorry about that. We have to change the implementation in the k omega model. So we will go to the k omega model. Let's just do it by terminal. Oh. Just make it full size and find this correct function. Okay, let's see the changes he's asking for. Well, what has he actually changed here? So I have this the same. Oh, eddy viscosity, correct. So it wants me to affect the eddy viscosity correct, while he asks for basic turbulence model correct. That's the change, right? Basic turbulence model. Okay. So I think all of this is the same. Comment this line out and add this. So that has been committed, that change. Right. So let's prepare for this compiling and getting a lot of errors. I don't know, I already had the turbulence model, so okay. Okay, so that has updated my files. And now I'll go here, and I'm going to essentially try a wmake. Okay. I think I don't have a case where this works, so I probably should do what he has done. And okay, let's do one thing. I will do one thing. I will make a video of this and share it with you, or at least share the files if I can do what Mr. Nielsen has done here. Because essentially he's changing the diffusivity function and all this. Okay, but these changes are very specific to whatever you are going to do to try to run the turbulence model. What I want you to understand is there is a very unique way to sort of compile a turbulence model, and I'll just go over it once more. And if you have any questions, you are welcome to ask them. I will also try to figure out why one approach worked and the other not, and I'll give a clarification in the Teams group itself. But essentially, the reason why I'm focusing more on the compilation part is because changes anyway you will make to your own turbulence model based on what you have to do. The more difficult part or the more complicated part regarding OpenFOAM is actually being able to compile the turbulence model and having it run in your case. So that we have seen today. I'll just go over it one last time, the entire process. So I will start with the main OpenFOAM directory structure. So as I said, in SRC, you have this folder called turbulence models. And within this, the small t turbulence models contains most of the standard k epsilon, k omega, realizable, renormalized group theory, whatever, like all these typical models. The LRR model is also here. They're all in the small t turbulence model folder, but they don't get compiled even from this folder. I mean, they don't get compiled from this folder or any other folders here directly. Like in none of those folders, you will find some make file. A make folder with files where it says that you have to compile ras/k omega. And the reason for that is that you can't simply compile it without knowing the other templates that need to be used. So it has to be a template sort of class compilation, and that is why what you have to do is you have to compile it from here. So here you have this compressible folder wherein you have turbulent fluid thermo models. Within that, there is turbulent fluid thermo model and turbulent fluid thermo models plural. The plurals.c file is where you actually have this make RAS model, the compilation. So the other thing that you saw is you can compile, but it still doesn't recognize your model. So I still have a feeling it's got something to do with the fact that I am messing up the compressible and incompressible. I mean, something within that fact that I was running simple form, but I ran I include most of the compressible directories. But then OpenFOAM actually compiles from that folder, like from the compressible folder, regardless of what model it is. So I'll figure out what that mistake was, and I will share it in the group. Also, I will share, if you want to go through, this is actually a reasonably good exercise. To go through this, it's a 23-page document and it's not very straightforward, but essentially it will have similar themes to whatever I was talking about. And this is a problem. Like, you might think that I am making a hack by trying to compile the turbulence model in this way. But not really. The implementation of a new turbulence model is actually not a very easy thing compared to implementing a function object or implementing a boundary condition in OpenFOAM. So it kind of needs to follow this basic principle that you have to follow. I mean, it's easier to do it if you follow the directory structure exactly as it is in the src / turbulence models folder. So the next thing that we did was we tried to create this exact directory structure where we had the main k omega code in RAS in turbulence model capital T / turbulence model small t / RAS. That is where we kept our files for the main turbulence model definition. And then we created a compressible folder one level higher, and therein we had this folder, and then we had this file. So now I'll side by side open this. So I created an SRC, I created turbulence models. Wait a minute. What happened to the... Oh, sorry. This run, within run. Yeah. So you have this turbulence models. And this for now you can ignore, but essentially I have compressible, I have turbulence models, and within compressible, I have this folder here, and it has this file. I changed the name of that file so that I don't want the same file name as this. I added my to it, and essentially I commented out the creation of all the other models and added my model's name here. That was sort of after creating the directory structure, and which was the first step, and the second step was adding the files for k omega and renaming them to my k omega everywhere in the naming of the files folder and within the files. Then this was step 3. You create this file, you edit it out so that you only have the model that you need to make after changing this name. And then you have this sort of make, wherein options you can directly copy from here. Although I will give a clarification of options, there may be some other sort of libraries that I didn't add, but files is clear. You only need to include the name of the file that has the make RAS model, your model, whatever your model's name is, that line of code. So that needs to be compiled. And yeah, after that, after you have done that, what you will need is you will need a set of files in here in an ln include folder. So you will have to run this command. Yeah, essentially this command at the pertinent folder. So I think it was this. So in this, I had to run the command, and that creates this ln include in turbulence models where you have these files, and now these will be actually referred to when you are compiling this file. And then finally you just run wmake, and that should compile. It will take a bit of time to compile because as I said, it will essentially have to compile all the possible combinations of transport models that it will use, and that is why it will be a long process, and that is also why it cannot simply have one single implementation, and it has to be sort of compiled indirectly. Okay, so from my end, what remains is to share this set of files and with an explanation for why one set of compilation files worked and what didn't. And I can give you as an exercise something else where you have to make some changes. So what I will try to do is I will try to give you a complete list of changes you have to make to one model to generate another model. So I'll have to go back and look at some turbulence model I had changed. Um, and then as an exercise, I can give you a second set of changes to make on your own. So that I can do. I can sort of give this exercise with sort of a tutorial before and an exercise later. So meanwhile, if you have any questions, I know this is already going to take a lot of time to digest. So if you have any questions on the top of your head, you can ask. Um, Otherwise, I mean, the compilation process I have showed, but um, for any specific model, I mean, that will require some other changes uh, that is very particular. So generally, it depends on what turbulence model, what transport model your turbulence model is going to be used in, and accordingly, that may change the implementation. So that is why I want to give you one exercise, one tutorial and one exercise regarding this. So that I can do. Um, yeah. Uh, so if you have any questions, you can ask now. Okay, I am actually. Hello. Okay, let me see the chart if there is anything. Jamshid. Wait, he has just asked this. Is it the last turbulence session or will you continue? So, I mean, initially the plan was I would be one of the more regular people, but actually now I'm working somewhere. So it's more difficult for me to do this. And unfortunately, you have seen that I am not able to even keep my schedule very well. So there is always something cropping up. But what I can do is if you ask questions on the forum, I can try to answer those. And if there are enough people who have a similar problem, then maybe in the future I can conduct another session. Because see, turbulence models, the issue is that there is a, first of all, there is a huge variety of turbulence models, and generally what you can do is something that is relevant to everyone. So sort of compiling a turbulence model is something that is common, but generally the doubts that people have is very specific to their research. That requires like trying to have a more one-on-one interaction with that person. Yeah, I mean, I wish I could have done more in terms of turbulence theory, but then again, that is better served in a theory class, and it won't happen in like even 2 2-hour sessions. Like pure turbulence theory will, I mean, it's a never-ending field. So yeah, right now, if there are any more questions, okay, we can do one thing. People can just tell me what are some of the common like issues where they actually have to compile a turbulence, or what are some of the tasks where you are feeling like which turbulence model you are actually looking to modify, or there must be some theory or research that inspires your work in this field. So I would like to know that part, like where are people going to be implementing turbulence models or modifying or whatever, creating user defined turbulence models. So if anyone has that, Akshay's hand is raised. I don't know.
Hello.
Yeah.
Sir, am I audible?
Yes.
Sir, I have a question
Yeah.
regarding this, I mean, creating models. Sir, recently I was working with one of the solver, Interform,
Interform. That is the two-phase.
VOF based, volume of fluid based
Yeah.
solver.
Two-phase, right? Interform, I think
Yes,
it's
sir.
two phases. Yeah.
Yes, sir. So there is implementation of the surface tension model.
Okay.
Uh,
Yeah.
yes, sir. So there was one of the research papers, and I wanted to include a small piece of code in that particular surface tension model. So I implemented that piece of code, and I was successful in compiling the new model as well.
Okay.
Okay, sir, but I want to use that model into my solver.
As in
So
you are not using
uh,
Interform. You have made your own solver, or like I'm. What do you mean by my
yes, sir.
solver? Okay.
It means I have a different problem for which I wanted to use uh, the new surface tension model that I have created after having a reference from the research paper.
Okay. And
So,
so
sir,
you are facing an issue similar to what we faced, right? As in your model is
yes, sir.
compiling, but it doesn't show up when you actually try to run it, right?
Yes, sir. I
Something like
mean,
that.
I am not sure whether directly including the .h file will work, or I have to include it in the control dict file as you did here.
Okay. So yeah, I mean that is obviously one of the first things you have to do. So in control dict, whatever new library you have created, I'm sure that is a library. So there will be
Mm-hmm.
a .so file which you see when you finish your compilation, right? You see something like
Yes,
this right at the end. So this
yes.
exact thing has to be included in your control dict. Um,
Okay.
so I will show where it was. Uh, so where did I do this now? Um, did I run the model here? Yeah, this is the case, right? It's daily my k omega. This one. So you see in system control dict, this is the first thing that has to obviously be there. This is necessary. You have to include this, and anything you implement has to be included, because I'm hoping that you are by default creating in foam user app bin or foam user libbin rather than foam app bin and
Yes,
foam
sir.
libbin, right? So if
Yes, sir.
it's
User
not
have.
in foam app bin and foam libbin, which is actually what you should be
Mm-hmm.
doing, it has to be included explicitly like this.
Okay.
But then even with surface tension models, I'm not sure, like it might be a templated class that you must have copied from.
Yes, sir. It's a
So
template class.
right, so then it matters whether your like, so for example, where I am failing to right now compile is, I believe that I am missing some incompressible incompressible transport model inclusions
Mm-hmm.
in my compilation. So something like
Mm-hmm.
that, if you have also messed up, it's possible that
Yes.
that is why you are not seeing it in your solver. Your solver is supposed to be sort of maybe
Mm.
multi-phase or more than two phases or something like that, and that
Yes.
version of the of your surface tension model has not been compiled.
Yes,
So
sir. But as we can see in this turbulence model, we have to choose the turbulence model whether we want to use the k omega model or the new one that we are selecting. But in
okay.
case of this interform solver, we just have to give the surface tension coefficient value. Apart from that, we don't give any explicit information. Then how to
Okay.
deal in such cases?
Okay, so I am not completely sure how the surface tension model has been implemented. I had a friend who was working on, he was not necessarily working on creating his own surface tension model, but he was working with Interfoam. I will have to look into this. I don't know. I mean, if Pratyush is still there, I would ask him to answer, at least tell you which sort of this thing will be relevant to you, because uh, I'm sure that you can always change it in the solver. You can always make a solver that adjusts to everything. As in,
Yes, sir.
you can have a solver with an additional implementation of, you can create a different field of surface tension, and then that field will you be used to add a term to your main u equation or t
Yes, sir.
whatever t equation, that you can always do. But if you want to
Yes, sir.
use it like more generally, then you will have to look into the actual implementation of the surface tension model, how it has been carried out, and then there you will
Yes,
have
sir.
to make a change, right? So I'm not the correct person for this. I believe Pratyush has some classes planned for multi-phase, because I think he also has some experience with Interfoam. So
Okay.
it's possible that he might have something planned. Um, well, is he still there? I don't know.
I think he is not it.
Okay. Anyway, so yeah. I mean, see, if nothing's working, you just try to make it work first. So then you should do something like that, like something equivalent to
Yes,
the
sir.
surface tension term in the
Mm,
U equation and T equation. You just
mm.
create a field that eventually you manipulate to get that term and then add it to U equation, right? Or
Okay.
whatever term.
It means instead of making the library itself for the surface tension model, I just need to include
Yeah,
I
because
mean, I just need to include it in the equation of the
the
solver.
reason why I say that is because you are already mentioning that you are creating a solver as well, right? So
Yes,
you are
I
already
have to.
doing a custom solver creation. So if you can
Yes.
exactly pinpoint where the surface tension model is coming into play, like in
Mm,
which term, then you might
mm.
be better off just including everything in the solver. Unless you have a plan to do something more generic, like you are planning to use that surface tension model with several types of solvers. If your research is
Uh,
more focused, just make it work
yes,
right
sir.
now this way.
Okay, sir. Thank you.
Yeah. If there is any other question, otherwise we can anyway wrap up, because I know I started the class late and I've already postponed it. So yeah, we can end the session here. So I'll just hang around for another couple of questions. If there is any question, I'll wait. Um, so I'll wait like 20 seconds. Otherwise, yeah, we can all finish the call. Yeah. So my question broadly was, I mean, if you don't have any direct questions, still you can just tell me where you are implementing a turbulence model, or what exactly is your research where you need to do this.
I was trying to implement a large eddy simulation in a vortex cavitation situation.
Okay. So you are trying to create a new subgrid model. Like, is that your goal, or you are just trying to run an LES with any of the already available models?
At first, I'm just trying to run it, and then if modifications are required, it is not matching the experimental values, then I'd have to modify.
Okay. So, what is your experience so far? Are you experienced with running LES with OpenFOAM, or you are new to it?
I am new to alias. Mostly, I have done mostly WAV DNS simulations.
Oh, okay. Um, okay. So, LES, yeah. I mean, LES, DNS has its own challenges, but yeah, I mean, LES, then there is a lot of grid related work you have to do. And yeah, I mean, eventually you will have to try different SGS models as well. Um, because,
Just one
I mean,
question related with the grid. Uh,
yeah.
uh, how do you make sure that that grid is sufficient for LES? Or LES and RNS grids are different?
Yeah. So, I think last class also there was somebody who asked this,
Yeah,
but
somebody has asked. Yes.
yeah. So, as I said, typically, um, there are ways to even figure out what is a good starting point for RANs. But let's assume you have an idea where you got a converged RANs solution, like grid independent RANs solution. Okay, I'll start with a rule of thumb. Generally, there are some what do you say, the based on the turbulence intensity or things like that, there is a rule of thumb that if your characteristic scale is let's say D for the flow, for the turbulent flow, the most energetic eddies will have something like D by 6 to D by 10 as their size, right?
Okay.
So RANs should roughly be able to capture their dynamics. If it's very coarse, if it is, let's say, D by 2 in size, the cells, then obviously there will be too much of averaging, too much of dissipation. But roughly you can start as a starting point, use something that resolves, let's say, D by 10. So for D by 10, you can go to D by 20 or let's say D by 15, something like that is your spacing in the first set of RANs calculations that you do. Now in RANs, you need a grid independent solution, meaning you have a solution, you refine the grid, you again run the simulation, and you get no difference. So that result you should get. Once you have this, your RANs work is done. You have a grid independent RANs solution. Now what you do is generally you can use the RANs result to estimate a turbulence length scale. So if you're using K omega or K epsilon, something like this, there is a combination of K and omega that gives you the length scale. So K is equivalent to the square of the sort of turbulent fluctuations, the square of the velocity of the turbulence. So it is sort of U dash square is what K represents. And then if you're using, let's say, epsilon, then epsilon represents the rate at which U dash is getting dissipated. So it is U dash square, sorry, U dash square is getting dissipated. The turbulent kinetic energy is dissipating. So U dash square into U dash by L. It's supposed to be basically what epsilon represents roughly. So it's U dash cube by L. So you can use a combination of K and epsilon. So let's say you've got a solution. You have K and epsilon throughout the grid, right? What you can do is plot this in paraview. And then in paraview, you can use a calculator where you get the value of K raised to 3 by 2, which will give you U dash cube because K is U dash square. So K raised to 3 by 2 is U dash cube divided by epsilon. So that will give you an estimate for L, the turbulence length scale.
Right.
Okay. So then you see that plot. Obviously, some regions will have very low value where K is almost 0. So, but roughly in the region where you expect the most dynamics, it will give you some idea of what the length scales will be like, the turbulence length scales. And then based on those values, you can have your first LES mesh.
Okay.
So you got a rough idea, right? You can sort of do it systematically.
Right.
And then obviously LES is not supposed to be grid independent. The grid is directly acting as a filter. So you still have to sort of keep, then for LES, your sort of rule of thumb is the Pope criterion. So if, I don't know if you're familiar with this, but essentially,
first time I heard that, yeah.
Yeah. So essentially you have the solution for LES. You will have the resolved U value. I mean, the U value that you get is the resolved velocity. And then you will generally have some expression through the subgrid model for the unresolved turbulence, subgrid kinetic energy. Let's say it's K. Okay. So then what you do is you have to plot U square by K or K by U square, whatever. And then you have to see that roughly the value of U square is 4 times larger than K. So it's like 4/5 of the energy is resolved and then 1/5 is not resolved. That is the sort of rule of thumb that at least that much energy has to be resolved for LES to capture the main dynamics. 80% of the total momentum or whatever, the kinetic energy has to be resolved.
Okay.
And
Makes
typically
sense.
there are papers where they say it should be 90 to 95% for a good result. So it's possible that you do satisfy Pope's criterion, but you are not getting results matching with experiment. So then you will have to go for a finer grid. So this is sort of the process you have to follow.
Right. Thank you.
Yeah. Anybody else just sharing your turbulence experience or challenge in OpenFOAM?
If nobody has question, I would like to ask another question that will be a little personal, if that is okay.
Depends on the question if I will answer or not, but you can ask.
Yeah, I was seeing your profile and I think you have worked extensively on turbulence model, especially LES, right?
Yeah, mostly LES. But yeah, I mean, anybody who works in LES, like first a lot of time is spent in sort of doing some RANs related work. You generally LES with the initial RANs result, or as I said, figure out what the grid size should be. You have to get like a grid in.
Right.
So what was your question though?
Yeah. So like, have you completed your defense and everything? As you told
No,
that you are very busy.
no, yeah. So I have my sort of work is approved. I have to submit my thesis by the end of the year, and
Okay.
I mean, meanwhile, I'm already working somewhere. Yeah, I mean, I'm already working in not academy. I'm working in industry in
So you
Delhi.
already started and you're trying to compile your work.
Yeah. So I already had my sort of main presentation where my work was to be approved. So that is done. Essentially, with a couple of changes, I am supposed to just finish writing my thesis. That is mostly like I think 50 to 60% of that is done. But yeah, I mean, I have to finish writing by the end of the year, submit it, and yeah, I mean, after that, it's up to the panel how long they take um, for the defense.
So your present work is related with your whatever you have done your work in PhD?
Um, it is related to turbulence, but not
Turbulence.
precisely related to. So, like my work was completely in jet noise, supersonic jet
Okay.
noise, but I am sort of working more in a broad aerodynamics field, high-speed applications, but aerodynamics, not necessarily noise.
Okay. That's all from now. Thank you.
Yeah. Okay. Okay, if there are no questions, then we can just finish the call here. Yeah. So I will keep myself online for another couple of minutes, but if you don't have a question or that's all you needed, then you can sort of exit the call.